Hello, today I would like to dive a bit deeper into the absolute orientation problem and derive the solution of how to compute the parameters of a similarity transform between 2 point sets. So this lecture is interesting for you if you, for example, have always wondered why in the ICP algorithm you're using the singular value decomposition in order to determine the rotation parameters between the transformation of 2 point clouds. Or this is also relevant if you ever considered to build a photogrammetric model. That means building a 3D reconstruction from camera pairs, and then you want to relate the photogrammetric model that you computed with an external reference frame where you have 7 degrees of freedom to commit to, that is the translation, a rotation, and a scale parameter. So what we want to do today is we want to derive the solution that we can compute for obtaining the absolute orientation. So how does it look like? Absolute orientation means we have a set of points x and we have a set of points y. So this is my point x and my point y, and I want to transform the point set x with a transformation of that style. That means one scale parameter, one rotation matrix, and a translation vector, so that the points xn are transformed to points xn bar in a way that these xn bar and the yn are as close as possible to each other. And we assume we have known correspondences. That means a point x1 corresponds to the point y1, x2 corresponds to the point y2, and so on and so forth. And what we then want to minimize is actually the Euclidean distance between the points yn and the transformed point xn. We may not necessarily commit to the Euclidean distance. We may also use a weighted distance if we want to give a different weight, for example, to one of those points. So, but let's start with this formulation and ask us, why is this relevant? Why should I care? So solving this problem is something that you need, for example, if you work with cameras and you have just camera images, you extract feature points from camera images, you find corresponding points, you compute the relative orientation of the cameras, and then triangulate the points back into the environment in order to get a 3D model of the environment. Then this 3D model is only defined up to a similarity transform. That means you do not know where that 3D model is in the real world, and you don't know anything about the scale. And in this case, the absolute orientation helps you to fix this, given that you have a few control points. So a few points for which you know their 3D location in an external coordinate frame. So the absolute orientation kind of anchors our photogrammetric model in the real world. This is also relevant if you work with LiDARs, for example, and you generate point cloud data, and you want to align point clouds with each other, for example, for registering point clouds. In this case, you typically don't care about the scale parameter because a LiDAR typically provides you the correct scale, but you still have the other remaining 6 degrees of freedom that you need to fix. This is a rigid body transform, but it's just a special case of the similarity transform. So if you have understood how that works with the similarity transform, you are also able to do the same for the rigid body transform. So this process that I will present here is also the key ingredient of the iterative closest point algorithm in order to understand why the transformation that the iterative closest point algorithm executes at every step looks the way it actually looks. So let me provide you with 2 examples. First, let's start with camera images. So what we are there we typically have our points computed in some frame from our camera, and we want to transform those 3D points in our photogrammetric model into an object frame, so into an external reference system that is provided. And we do this via the rotation matrix, scale parameter, and the translation vector. So in the 3D world, this is a 7 degree of freedom transformation that we need to estimate, and that means we need to have at least 3 control points, better more. Control points are points that we have in our photogrammetric model and for which we know their actual 3D coordinates in the real world. And if we know this, if we have these control points, then we can compute these parameters here, underlined red, for our absolute orientation. So as an example, so let's say you have 2 cameras, they're looking into the world and you see corresponding points in your image. what you then can do, you can compute the relative orientation of the camera pair. That means you can estimate where camera 2 sits with respect to camera 1, except of the baseline, so except of the scale parameter. This gives you two camera orientations. Based on these camera orientations, you then can do a triangulation and triangulate those points in the real world, which will give you the 3D locations of all those points in a local reference frame that is defined only up to a scale parameter. And of course, we do not know where that Euclidean frame sits in the real world. So in the end, we have this photogrammetric model, and we don't know the link to the missing external reference frame. And if we then have control points, that means some of those points for which we know their 3D location in our object frame, for example, those 3 points over here, then we can actually establish this missing link. And that's something that we are going to do today. So trying to estimate the rotation, translation, and scale parameter given we have those corresponding points. So in our example, our corresponding points would be these 3 points. So I can estimate R, lambda, and t, and then also transform all the remaining points. This again is also relevant if we work with 3D lidars. So if we want to perform point cloud registration, for example, here we are interested in finding a rigid body transform that transform one point set into a second point set. So for example, if we have here this green point set, which is in this case a 3D point cloud taken in an underground environment, and we are taking new observations, these blue skins, and want to register them with respect to the existing model. Under the assumption that we have perfect data association, this boils down to estimating the rotation matrix and the translation vector that tells us how the blue point cloud needs to be transformed in order to line up with the green one. And so that is a task that is done within the ICP algorithm and is something for which we exactly need to solve the same problem that we are addressing here today. And what I want to do to explain you now really in every single step is how to obtain this R, this T, and this lambda parameter. So our more formal problem definition looks like this. We have corresponding points yn and xn, and we want to transform the points xn so that xn and yn are as close as possible to each other. So we have those input points, and here we assume that the same index n from 1 to capital N provides us the data association, so those indices are correct. Point 1 is the identical point that we want to transform. And we can assume to have weights. If we say one correspondency, I want to give a higher weight. This can, for example, be used if I have uncertainty information about points. At least if I have isotropic noise, I can take that into account. So we have one weight for every corresponding point in order to weigh the importance of this corresponding point. This could, for example, be 1 divided by the variance of the point if you have an isotropic uncertainty. And that, well, then the task is we need to find the 3 parameters lambda, r, and t, where those 2 are 3-dimensional, and this is a 1-dimensional parameter, so we have 7 degrees of freedom, to come up with this similarity transform, so that the result of these transform points, these x bar, are as close as possible to the original point cloud to which I want to transform it to, so yn, and we don't take the pure squared error into account, but the weighted square error. I want to minimize this term. And the whole lecture here today is about how to find lambda, r, and t so that this holds. And we really want to derive this from scratch, and so that you have an idea on how to compute it, what's behind it, what are the assumptions which are behind that approach, and can apply this also in order to, for example, understand how the iterative closest point algorithm actually works. Okay, so the first step that we are doing is we want to change our coordinate system into a kind of a local coordinate system, and this should be defined by the point cloud yt, and we want to do that in a way that the center of mass, so the mean computed over those points, yn, is the origin of our coordinate system. So we want to do a shift in x, y, z, or in x, y, if we do this in the 2D world, in order to make a shift of those points so that all the points can be provided in this local reference frame. So we are basically just expressing this relative to the center of mass of the point set yn. So this can be easily done. I can compute the weighted mean. So I don't take the center of mass into account, but the weighted center of mass. So giving points which are more important, higher weighted here. So then the resulting minimization problem can be exactly formulated identical to as before. Yn minus x0n is the remaining part plus 0n. So I subtract 0n, sorry, not 0n, y0, I subtract y0 and add y0. So it's the exactly same problem, but what it actually means is that I'm reducing these points through a shift and these points through the same shift. Okay, so now I want to actually minimize this function over here. And the next thing I'm going to do, I want to actually rewrite this term, or these two terms here actually, so that we have a slightly different form. This will be turn out to be useful later on. So I want to start with my transformation, and I have my shifted transformation. That's exactly what I've explained to you before. And what I now want to do is actually want to move this t and y0, so those two constant vectors, I want to move it inside this xn so that I can also multiply it with the rotation matrix. So that means if I don't want to change this expression over here, but I want to move those two elements into the bracket over here, I need to multiply them from the left-hand side with R transpose, so that R times R transpose gives me the identity matrix, and I don't change the expression over here, but I've moved those quantities in here. And what I then can do is I can just define a new variable, call it x0, which is given by R transposed y0 minus R transposed t. And so if I do this, I can simplify this expression over here. This is actually, this is correct. I can simplify this expression over here that I have here xn bar minus y0. So this is the origin defined by the xn's. And I have a second variable which I subtracted here, which now sits inside that bracket. And what I've done, I basically introduced a new unknown x0, which replaces the translation vector. So I now want to estimate this x0, and if I have x0, it's clear that I can retrieve the translation vector. And I do this because this allows me to later on do some of the manipulations in an easier way. Okay, so having done that, we can rephrase our problem as this problem over here. So we have the transformation, transforms my points xn into this new frame. And I then do, in this expression, divide both sides by the square root of lambda, the scale factor, in order to get some term which then will be more symmetric later on. So I divide by lambda, square root of lambda, so it's lambda to the power of minus 0.5, and here lambda 0.5, and have my remaining expression that I have. So now my unknown parameters is this lambda, this r, and this x0. And so the goal is to find those parameters so that my original equation is going to be minimized. And I want to minimize the squared error over here. So what I need to do, I can now define my objective function, which tells me how those parameters change my error. So here is my objective function, and this is just the expansion of what we have done before. So this is exactly the transformation, so this is exactly this term that we wanted to minimize. So this was an inequality. The only thing we do, we are replacing these points, so the target points we're mapping to, with the points yn, where I want to be. And then it's not an equality anymore, unless I find the perfect transformation and I don't have any noise involved. But by replacing this guy here through an yn, it turns into a minimization task. So therefore I have yn sitting over here. And I'm again summing over all points and computing this product, which gives me the square distance weighted with my weight pn. And I want to minimize this objective function. So and if I minimize this objective function, so finding the parameter x0, lambda, and r, that this function is minimized, then I have found my transformation, which minimizes the mismatch between the transformed point set of xn and my yn. And that's what I actually want to have. So the key question is now, how do I minimize this function? How do I minimize this expression over here? And this is what we are going to investigate over the next couple of minutes here. So how to minimize this function. How do we minimize a function in general? We can compute the first derivative of the function, set the first derivative to 0, and then solve the remaining expression or equation, and then this provides us with the solution for the parameters that we're looking for. So what we need to do is we need to take our objective function here, compute the first derivatives with respect to x0, with respect to lambda, and with respect to r, set those derivatives to 0, and then solve the remaining equations. We will actually do that only for x0 and lambda, and will resolve the rotation matrix in a different way. But for now, we are approaching this problem by computing the first derivative with respect to x and with respect to lambda. So before we do this, we can kind of slightly rearrange the terms over here. So we take our objective function and basically expand the brackets over here, so we can set it up into individual parts. So I basically can break up the sum into 3 sums. The first sum only contains the y-ends. The second part contains only the x-ends, and the third part contains y-ends and x-ends. And this is kind of standard math to expand this expression into this expression. So to note in here, the first line over here doesn't depend on x0 and it doesn't depend on r, so it only depends on lambda. The second term does not depend on r, so it only depends on x0 and on lambda. And the first one is actually independent from lambda, so it only depends on x0 and r. And especially this is something that only this expression influences r, or r has only influence on this expression. That's something that we will actually exploit in the last step when we want to find the optimal rotation parameters. But let's start solving for x0, then for lambda, and then finally address on how to solve r, how to determine r. Let's start with solving for x0. So what we need to do, we need to compute the partial derivative of my objective function with respect to x0. So I have my objective function, that's just copy-pasted from the previous slide, and then we need to compute the first derivative with respect to x0. So we're taking this term and deriving this expression with respect to x0. So the first term actually gets eliminated. The second thing, this is basically, this leads to a square. So we get the 2 over here, and then the linear term over here, and the last expression depends linearly on x0, so only the part over here is the remaining part. So then we have computed our first partial derivative, and the next thing we need to do, we need to set this partial derivative to 0. So if we take our partial derivative, d phi by dx0, and set it to 0, then we are obtaining this expression over here again, just a copy and paste from the previous slide. So what we then can do, we can move one of the expressions, one expression to the other side and divide it by 0, and we can also move this rotation matrix out of the sum because this is constant, doesn't depend on the index I, so that we then get this expression over here. And now we can exploit the effect if you're kind of looking to this expression over here. So this is kind of now the interesting part. Because if we looked at it, what are we doing here? So what we have here is actually the mean of my points, yn. So what I'm doing, I'm subtracting the mean from every data point that I have, and then I'm summing those values up. But this is already the mean of those points. So if I'm subtracting the mean from every data point and then computing the mean again, I will obviously get a result of 0, right? Because if I compute the mean, subtract the mean, and then compute the mean again from the subtracted values, I should end up at 0. So this is something that we can exploit, that this expression over here must be 0 just by design. If this expression is 0, of course the whole part here turns into 0, and I know that this equation must be 0. So what results is then that the sum over all points xn, the scale factor times the difference, the mean subtracted, or the variable subtracted by xn times the weighting should also turn out to be 0. So I can just, again, take this expression and then expand the sum of the bracket with the sum, move it to the other side so that I then get the result that, and I can, that this is my result. So the sum over all xn times Pn divided by Pn. So this is nothing else than the weighted mean. So what I've done over here, I also divided by the scale parameter, which is only allowed if the scale parameter is unequal to 0, but we can assume that a scale parameter of 0 would anyway be a degenerated solution. That's something I'm not interested in. So I can safely assume that lambda is unequal to 0. And in this case, it turns out that this x0 is just the weighted mean of the input point set xn. So this is kind of the first step that we have derived now, that this function gets minimized if x0 is the mean of the input point set, the weighted mean. And that is something which you see, for example, in the ICP algorithm. What you do there is you compute the mean of the point set of the one point set and the mean of the other point set and subtract those means. And we have defined this only for yn, because this defines our coordinate system. And now we have derived that we need to do the same thing for xn. And we need to do that because we want to minimize our objective function. So this is kind of the first result, which basically tells us something about the translation vector, that I need to compute the mean of my input points, which is one step for defining the translation vector over here. And so the next thing we have to do is repeat the same process that we have done for x0 now for my scale parameter lambda. So we don't compute the first derivative with respect to x0, but we are computing the first derivative with respect to lambda in order to determine the value for lambda. So we again start with our objective function as we had it before, and now compute the partial derivative with respect to lambda. So here we have lambda as always kind of a constant scale factor in that sum, so I can move it out of the sum. So I have one expression over here where it's lambda to the power of -1, which turns into minus lambda to the power of -2. And this is here a linear term where lambda will disappear and the rest will stay the same. So that is this expression over here, rather straightforward. And then I need to set this value to 0. So I take the first derivative with respect to lambda, set it to 0. This is my resulting equation, and we can see very easily we can move this to the other side, multiply it by lambda squared, and then again divide through it through this expression that we move to the other side, and then take the square root, so that this is the resulting equation for lambda. So what does it mean? We have here the spread of my point set yn with respect to its mean, and here the spread of the point set xn with respect to its own mean that we just computed. We always kind of weighted with the importance of that point. So we are basically taking the spreads, the variance of the point sets with respect to their mean into account in order to determine the scale parameter. And again, as long as we are considering here only positive scale parameters, this is a unique solution that we get as long as the points, of course, have some spread and not all points lie exactly in the same position, then we, of course, cannot compute the scale parameter. But then this is our solution. And the only thing we need to know, we only need to know the point sets xn and xy, so my input point sets. We need to compute the mean or weighted mean of those point sets, and then the rest can be computed in a straightforward fashion. So with this simple equation, we can directly obtain the scale parameter here. So the difference in scale between our photogrammetric model, for example, and the object reference frame. So let's come to the last parameter that we need to determine. The last parameter that we need to determine is the rotation matrix. So how to obtain the rotation matrix. And here we take a slightly different approach if we look into the rotation matrix that allows us to effectively minimize the function by finding the optimal rotation parameter. So we want to find the optimal rotation parameter that minimizes my objective function. And now let's have a look to this objective function, and we can actually see that the first two expressions over here don't depend on r at all. So the only part which depends on r is actually this expression down here. So what we need to do if we want to kind of minimize this overall term, we need to maximize this expression without the sign over here. Or actually, this 2 can also go away. So if we can maximize this expression over here, so finding the rotation that maximizes this term, then we have found the rotation matrix that minimizes the overall term over here. So what we need to do is we need to find the R that maximizes exactly this expression. So it's my R star, my best possible rotation to find. Under the constraint, of course, that R is a rotation matrix, so R transposed times R must be the identity matrix. Okay, what we can do, however, we can exploit the information that we have so far. So we can exploit my x0, my y0, and my lambda parameter. And we do so by computing reduced parameters. So or reduced coordinates called an and bn. So an is basically the difference between the points we want to map to, xn, subtracted by the mean, multiplied with the 1 divided by the square root of lambda. So lambda already determined, this value already determined, and it is the same for x. X0 already determined, this lambda already determined, so we can directly compute those values a and b. And then this leads me to kind of a slightly simplified form of writing this down. bn transpose times RAN times the weight vector is the function that I want to maximize. So I need to maximize this expression over here. And now we can exploit the fact that we can actually rewrite this expression over here. So for vector, my rotation matrix, another vector, in a form that uses the trace, so the sum of the diagonal elements of a matrix, and it's a matrix which is given by this exactly same rotation matrix and the matrix H, and this matrix H is basically built up from this B and this A terms over here. And this is the cross-covariance matrix, so sum of all elements with the product of AN times BN transposed, so this will turn into a 3x3 matrix, and of the points together with its weight. So what we're doing, we're computing the cross-covariance matrix, and if I take this cross-covariance matrix H and multiply R left hand to H, compute the trace, I actually have exactly the same expression over here. So what I can do is I can try to find the expression which maximizes this trace. So that's what I want to do. And we want to use for this maximization the singular value decomposition. So it's something, if you have seen the ICP algorithm, for example, you may have wondered where this SVD, the singular value decomposition, comes from. And as we will see here in a second, it becomes very useful for us to use the SVD because it allows us to decompose our matrix, H, and then define a rotation matrix that we can then show maximizes this overall term. And that's exactly what we wanted to do. So the goal is what we want to find R that maximizes the trace of R times H, where H is the cross-covariance matrix, and we can do this via the singular value decomposition. And we actually show that to you. That's actually not very difficult because just the singular value decomposition allows us to define a rotation matrix which then has certain properties which are advantageous for us. So we start with a singular value decomposition of H, which basically means it breaks up the matrix H into 3 matrices, a matrix U, a matrix D, and a matrix V transposed, with the properties that U transposed U is an identity matrix, V transposed V is an identity matrix, and that D is a diagonal matrix containing all the singular values on the main diagonal, all being positive here. So typically it's arranged in a way that we have done things only in a positive way. Okay, so these are basically rotation matrices in my case, in my 3x3 example. This is a 3x3 matrix, and this is a 3x3 diagonal matrix. Okay, so we have this matrix U, matrix D, and matrix V transpose that we directly computed from H using the SVD. So SVD is only used to decompose this matrix into these 3 individual matrices. And now we can kind of use those individual matrices and the properties of these matrices in order to come up with a rotation matrix that maximizes this trace expression. And I want to do this in a way that I say, I just tell you what R looks like, and then we can actually prove that this is the optimal R. Okay, so let's take R and let's see what happens if we set R as V U transposed. So again, I'm telling you how to set this matrix R. So we take the singular value decomposition, so the matrix U and V that we get out of it, and use them to define R by setting R as V U transposed. And if we do that, let's see what happens. Let's see how argument or the equation with the trace changes if we set R in the following way. So in this case, the trace of R times H can be expanded as the trace of V times U transposed, because this is directly R, and then U dV transposed with H, which is the singular value decomposition of my matrix H. So if I look to this product over here, I can see that I have U transposed U sitting in here. And given that U is a rotation matrix, U transposed U gives me the identity matrix. So as a result of this, those two matrices disappear, and I am left over with a trace of V, D, V transposed. So by setting R in that way, my trace expression simplifies to this term over here. Okay, now can I make a trick with this matrix D? So remember, this matrix D here was a diagonal matrix. So it's a diagonal matrix which has only positive values on its main diagonal, at least as long as H has full rank, so rank 3 in our case. And as a result of this, everything is 0, only the main diagonal are positive values. So what I then can do is I can split up this matrix D in two identical matrices, called here square root of D. And this is basically the original matrix D, just taking the square root of every element in there. So taking the square root of the main diagonal elements, because all other elements are 0 anyhow. So I can write D as square root D times square root D, as it's written over here. And again, this is something which I can do because I know it's a diagonal matrix with the singular values on the main diagonal. So now do a further trick. I'm taking this expression that I have in here, and now I kind of want to move the transposition operator over those two matrices, so that I will end up having 2 times the same matrices over here, only once transposed. And I can do this because this D is a diagonal matrix which has only the positive elements on the main diagonal, so it doesn't matter from which side I'm multiplying that, so I can actually simplify this expression in this form over here, and can then define a matrix A as V square root of D, so that this expression simplifies to A transposed. So my overall trace expression, the trace of R times H, is nothing else than the trace of a matrix A times a matrix A transposed, where A being a positive definite matrix. So again, it's positive definite only under the assumption that my cross-covariance matrix is full rank, so has rank 3 for our 3D problems. And that's important to note. And if we don't do this, if it doesn't have full rank, we actually will see won't have a unique solution. Okay, so, but this is the property of my matrix A transposed, and I want to compute the trace out of it with A being a positive definite matrix. And what I then can now is I can exploit an inequality that holds for every positive definite matrix A, that the trace of AA transposed is always larger or equal than the trace of exactly the same matrix multiplied here with, from the left-hand side with an orthonormal matrix. So for us, a rotation matrix over here. So by adding a rotation matrix here in this term, this trace will be smaller or equal than this trace. And this holds for all rotation matrices R prime which are out there. And this is actually a result of the Schwarz inequality. But what it actually means is by putting any other rotation in front of this matrix here will make the trace smaller. So if we want to maximize a trace, we can't do better than keeping this equation, not multiplying anything here in front. That means the rotation matrix that I have defined by using the elements of the SVD was the best possible rotation matrix because it maximizes this expression. Any other rotation matrix I would multiply to that. Any other would be smaller or equal. So I can't do better than choosing R in the way that I have chosen, because the trace of RH is always larger or equal than the trace of any other matrix R prime RH. And this would be kind of put together in a rotation matrix. As a result of this, my choice of R was the optimal choice. So what I do is I choose R as VU transposed. So the optimal R, and this is the R that minimizes my objective function, my squared error function, is exactly this rotation matrix, which is built up from those two rotation matrices, where The U and V stem from the singular value decomposition, and this matrix H is the cross-covariance matrix built up from the vectors of my reduced coordinates together with their weight. And that is the reason why in ICP, for example, you use a singular value decomposition to break up your cross-covariance matrix and define your rotation matrix R. If it was unclear to you so far why this happens, what I've shown you here is the reason why we choose it, because it is the optimal R which minimizes the overall error, and it's a result from the Schwarz inequality. Okay, now I determined x0, I determined lambda, and I determined R, the optimal parameters that I have in here. The only thing I need to do is I need to come back to my original translation vector, right? But this is in a very straightforward way, just how I defined it, because I was using x0 as my minimization term, but x0 and the translation vector are tightly coupled with each other. So x0 is the rotation matrix transpose times the mean of the target point set minus R transpose the translation vector. So if this is known, R is known, I of course can solve this with respect to t, so this directly leads me to, this is y0, so the mean of the target point set minus R times the mean of my input point set that I want to transform. And this gives me the translation vector by how I need to shift my point set in order to minimize the squared error. And with this, we have derived all the quantities that we needed to derive. So my solution is, this is the scale parameter, this is the rotation matrix, and this is the translation vector, which minimizes the squared error. And all the terms I need to compute on the way is computing the mean over my point set yn given plus my weights. If I have weights, if I don't have weights, they all will have weight 1 divided by n. Of using x0, so it's the mean of my input point set. Then I need to compute the cross-covariance matrix by using the mean reduced coordinates of the points, and then I need to compute the singular value decomposition. And with those 4 computations, I can compute my scale parameter, my rotation matrix, and my translation vector that minimizes the error between the input point set transformed with this similarity transform and my point set yn. And it minimizes the squared error over here. So with this, I'm coming to the end, and I hope I have explained you how this minimization actually works. So we are computing the absolute orientation, or solving the absolute orientation problem, which is a key problem in photogrammetry, especially in 3D reconstruction. When you do a 3D reconstruction from camera images, where you don't know the scale, you don't know where those cameras are in the real world, the absolute orientation problem through a set of at least 3, preferably more control points in the world allows you kind of to anchor this photogrammetric model in the real world. And what we do, we compute a similarity transform that transforms 2 point sets into each other. And this is also something that the ICP algorithm uses, except that we don't need the lambda parameter over here. It's a least squares approach, or the least squares solution, in the sense that I'm minimizing a least squares function, although it's kind of not done the standard way, because I used this special trick with the SVD in order to determine the optimal R, and haven't done it by computing the first derivative, setting the first derivative to 0, as I did it for the other equations. This approach is fairly easy to implement, it's fast to execute, and it's one of the effective and very popular approaches in order to solve the absolute orientation problem. So I hope I gave you some background information why ICP works in that way and how to anchor a photogrammetric model in the real world, which is used in 3D reconstructions using ground control points, for example. So I hope that was useful and allows you to put concepts that you have seen in the past on better grounds so that you know why things are the way they are. With this, thank you very much for your attention.